electrochemical cells. Let's start with a little history lesson. The Weston cell was invented by Edward Weston in 1893, and it was being used for a very long time as an excellent voltage reference source because it consistently produced 1.0180 volts at 25 degrees Celsius. The output was stable and reproducible. There were some environmental drawbacks due to the use of mercury and cadmium in this cell. So here is the Weston cell. It was composed of an anode and cathode, and the saturated cadmium sulfate solution flowed between the two electrodes. There was a cadmium mercury side and a just liquid mercury side with a barrier here of mercury sulfate. So let's look at the cell reaction. The two reactions, the oxidation and reduction reactions that would be occurring, on the left-hand side, you would find that the cadmium mercury amalgam here would produce cadmium cations and 2 electrons. Thus the cadmium was being oxidized. And on the right-hand side, the mercury sulfate would take those electrons and reduce to become the liquid mercury and sulfate ions. So the mercury was being reduced, and the sum of those two reactions, with the electrons canceling each other out, is shown below here in orange. So what all this means is that spontaneously you get an electrical current occurring between the electrode on one side and the electrode on the other, and a voltage is produced. The shorthand cell notation for the Weston cell could be like this, and it was cadmium in a 12.5% mercury amalgam, and that would become cadmium sulfate. The single lines separate the phases of one of the electrodes, and the double line separate a salt bridge. Sometimes you'll put the salt inside this double line, or just indicate that there is some sort of separation between these two cells. And then on the other side you have the mercury sulfate and the mercury solutions. Note that the solid cadmium sulfate is necessary to maintain a saturated solution, but it does not participate directly in the reaction, so it is not included in the cell definition. So an electrochemical cell is an apparatus that allows a redox reaction to occur by transferring electrons through an external connector. So you need to have a complete circuit. If you think back to grade 9 electricity, you need to have a circuit with some sort of conductive material connecting a positive and negative end of a cell. Batteries are cells. Voltaic or galvanic cells are cells that are spontaneous, and thus the products are favored. And an electrolytic cell is a reactant favored cell, which is not spontaneous, and you actually use an electric charge to force the reaction in the reverse direction. Galvanic and voltaic cells are based off of two scientists who basically discovered them simultaneously. I'm sure you can go to the Wikipedia page and look both of them up. But Luigi Galvani and Alessandro Volta derived the cell and concluded that electrical energy from spontaneous reactions are taking place within these cells. Here is a very simple zinc copper galvanic cell, and let me break this down for you. So if you could start at any point in this cell, the difference in the potential of each reaction causes it to be spontaneous. So here electrons are moving from this reaction. So zinc is losing electrons and they're going into the copper, giving the copper a negative charge. Thus, the solid copper becomes ionized into this copper solution. Okay? So that the copper electrode doesn't have a charge anymore. The positive ions from that solution attach itself to the copper electrode, and you actually get solids starting to form here. Because this copper solution is losing copper ions, there's a deficit of positive charge, and this salt bridge contains a positive and negative ion, and the positive ion will go into the copper solution, and so that the salt bridge remains uncharged, the negative ion will go into the zinc solution. If this zinc ion solution starts to have a negative charge, then solid zinc would be ionized and go into that solution, producing more 2+ ions, giving a negative charge to the zinc, which causes the electrons to leave. And you get this whole cycle continuing to go through, and that's the complete current. That's that whole cycle. If you attached a voltmeter to this wire, you could measure a voltage that is going through this cell. So the zinc, as I mentioned, was going from solid to ions and producing electrons. Thus, the oxidation occurs at the anode, and that becomes the negative electrode. On the other hand, the copper here is gaining the electrons and becoming solid copper, and thus the reduction occurs at the cathode and is positive. And that is always the case. The reduction will always occur at the cathode, and the oxidation will always occur at the anode. Anion-cation movement is happening here, as I discussed previously. Here's another example where it shows a salt bridge that's kind of a semi-permeable membrane between two cells that are within one container. Voltaic and galvanic cells can look like this as well. This just gives another depiction of the electron and ion flow within these cells. Note it's a general, the reduced species is becoming an oxidized species, and the oxidized species is becoming a reduced species here. So you could put whatever metal electrodes you have into this cell, and you would get that same reaction. The electrode at which oxidation is occurring is called the anode, and reduction is called the cathode. In general, for cell notation, you write the anode on the left and the cathode on the right. A cell operating spontaneously in this configurement is said to have a positive total cell potential. In a galvanic cell, the cathode is the positive end, and in an electrolytic cell, the cathode is the negative end. So when we flip from the spontaneous to the not spontaneous, the positive and negative flip, but the reduction and oxidation don't change. The reduction will always occur at the cathode. Also, so positive cell potential will be spontaneous, and a negative cell potential will be not spontaneous. So this is going through the cell breakdown as well. We have a voltmeter here, and again, you could follow this path of electrons through the whole cell. In this case, it's the zinc and copper electrodes from the first example, but we have defined that it's a copper nitrate and a zinc nitrate solution, and that our salt bridge consists of potassium and chlorine. So I'm going to go through one more time. Let's start in this copper solution here. The copper ions become solid, giving a deficit of positive charge to this solution, and the potassium from the salt bridge goes into that solution so that it can be neutral. The chlorine will then go into the other solution so that the salt bridge doesn't have a net charge, and that causes the zinc to leave the solid and become ions into that solution. The then electrode is balanced by electrons leaving and going and joining this copper electrode to again cause that flow throughout the whole cell. An electrolytic cell is the same thing but done in reverse. So you force an electric current to cause the opposite reaction to occur. You force the electrons in the opposite direction, and everything happens in the same way. In this case, you have to have a cell greater than the potential that the cell produces. So in this cell, it was a 1.1 volt cell, so you would need to apply a current greater than 1.1 volts to force it in the reverse direction. This is much like equilibrium expressions, where if you get a certain concentration higher than a threshold, it forces that reverse direction. Charging a battery is just an electrolytic cell where you take electrical energy and convert the chemical energy in the battery to the orientation that would be spontaneous. And then that spontaneous reaction is the galvanic battery converting its chemical potential energy into electric energy. There are a few examples of cells that you can try on the worksheet attached to this lesson.